Okay, thank you. Let me start by thanking the organizers for the opportunity to give a talk here. This will just be an overview of some results that we've obtained over the last 2 or 3 years, basically, in the context of this kind of larger program. And since this is a more mixed audience, I don't really want to go into too much technical detail. Of course, you can ask me about it, but I want to focus more on the general ideas, also from the conceptual side. So the idea is basically already in the title. We're working in basically a discrete setting for quantum gravity, where we can think of geometry as kind of composed of discrete excitations, which we can picture as some kind of atoms, if we want. And then the proposal here is basically that the universe should be some kind of condensate of a very large number of these discrete degrees of freedom that are in some kind of coherent macroscopic configuration, and the goal is then to derive some kind of effective quantum cosmology dynamics more or less directly from a proposal for fundamental quantum gravity. So this is a work that we've started with Daniele Oriti and Lorenzo Sindoni in these 2 papers, basically, and there's some more follow-up work since then. So here's an outline of my talk. I will spend some time on the introduction and motivation of this approach, also comparing it to what has been done before in this more general setting of the connection of cosmology and quantum gravity. Then more specifically, of course, we need to have a concrete theory, a concrete framework in which we can actually do calculations. So this is the setting of group field theory, which I think is not really familiar to most people. So I will describe that very briefly as a potential framework for discrete quantum gravity, is very closely related to loop quantum gravity in a way that I will also make clear. And then I will show how to define these condensates. We are basically using intuition and also some mathematical language, basically from condensed matter physics, where you actually have a condensate in the lab of atoms, and so much of the intuition here will basically be by analogy with condensed matter physics. So hopefully this will become a bit clearer. But we will apply this then to the setting of quantum gravity, and I will show how and how you can actually do calculations with these condensates. And then the main goal is basically, in this part, is to extract some kind of effective cosmological dynamics, so something like a quantum cosmology model from the proposed dynamics of the fundamental degrees of freedom of quantum gravity. And then I will have a summary and outlook at the end. So I think there has been a lot of interest, especially in recent years, in the interplay between theories of quantum gravity and early universe cosmology. And I think the interest really works both ways. So if you're working on quantum gravity, of course, one day you have to be able to come up with some kind of observational test of your theory. And I would claim that the very, very early universe observationally, because the energy scales become high enough for some kind of effects of quantum gravity to be potentially at least relevant. So this is the interest of quantum gravity people, to say something about cosmology. I think also, on the other hand, there can be some input from quantum gravity that can be helpful for cosmology. So in standard theoretical cosmology, we know that there is still a Big Bang singularity, which we have to resolve at some point, so we have to understand how that works, and we would most naturally turn to a quantum theory for that. More specifically, if you're interested in inflation, there are many theoretical issues that people debate a lot, like the choice of initial conditions, the precise shape and form of the potential for inflation, and fine-tuning issues, and so on. And then you might have the hope, at least, that some input from quantum gravity could help you in constraining these things a bit more. So then, if you're a quantum gravity person, what you should do in your favorite theory, whatever it is, you should be able to describe a universe that's relevant for cosmology. So it should be something like a almost homogeneous and isotropic universe with perturbations, and in particular also time dependent. And you should also, and this is perhaps the even harder part, you should be able to compute some kind of effective dynamics for these universes from your theory that you can then compare with, for example, the predictions of other cosmological scenarios, and of course, at the end of the day, also with observation. And I would say that this is in general a very hard problem. So we basically have one proposal towards this. A bit of history here. So since this is very hard, what people have done historically and traditionally in quantum cosmology is to work in the mini-superspace truncation, starting from Misner and Wheeler, DeWitt, many others, of course, where basically you assume at the classical level an exactly homogeneous continuum metric, perhaps isotropic, perhaps anisotropic, but you are left with only a finite number of degrees of freedom for geometry, which you are then quantizing, and you're developing some kind of quantum theory of these remaining degrees of freedom, which are only the exactly homogeneous mode of geometry, basically. So you can do that and then do calculations and so on, and this has been followed, of course, by many people over the years. Conceptually, you don't really know very much about what this really has to do with the full theory of quantum gravity, because you've removed so much of the degrees of freedom already at the classical level. So some progress was made starting from the work of Martin Boyewald by using some input from quantum gravity, basically loop quantum gravity methods in the quantization, but still in this mini-superspace context, so still a finite dimensional quantum mechanical model, but with a different kind of quantum theory, which leads to loop quantum cosmology, which has been, again, been followed by many people, and there's a lot of results, and we'll hear about it from Aurélien later this week. And there's one thing that happens right in the beginning. You can show that the Big Bang singularity is now replaced by a bound, so this is very nice. This singularity is removed. And you can do a lot of more things, of course. But again, the connection to the full theory is kind of unclear. And I would say there's no clear way in which you can identify these exactly homogeneous metrics that you have quantized with states in the full theory of loop quantum gravity. And there's a lot of ongoing work by many people, but I would say this is still not resolved in full. So one viewpoint that you can take on this issue, which is, I'm taking this from a recent review by Martin Boyewald, is to say that if you study a mini-superspace model in quantum cosmology, you can view this as a kind of quantum theory of a single patch of the universe. So you're looking at a very small, something like an elementary patch of geometry, which is homogeneous in itself, and you're quantizing that, and you might call this an atom of space, and then you're studying the quantum theory of that, and assuming that the universe is exactly homogeneous, you might think that the model you've developed in this way could be a good approximation to what really is the full dynamics of a large number of these patches. So more generally, you can imagine very inhomogeneous configurations, but you're kind of assuming that your configuration is sufficiently homogeneous that you can only focus on one of these atoms. And it's then also clear that this may or may not be a good strategy. You can think of examples where this works and examples where this really doesn't work very well. Sorry? So this is a canonical setting. So you have some kind of Wheeler-DeWitt equation, Hamiltonian constraint. And yeah, you live with the problem of time, absolutely. Yeah, I'm completely skipping over all the conceptual difficulties with this kind of quantum cosmology. I'll get to that at the end, I think, a bit, but not very much. So yeah, if you then take this viewpoint of this single patch model, there's a natural strategy in order to go beyond this mini superspace truncation, which is that you should really study some kind of many patch model. So you take not just a single patch, you take a large number of degrees of freedom of quantum geometry, potentially infinite, and you study this kind of interacting quantum system. Of course, in general, this will look nothing like our own universe. In order to look like our universe, these many degrees of freedom should be in some kind of particularly nice symmetric configuration. And if you then think about a condensate in condensed matter physics, this is basically what you would like to kind of imitate to some extent. So it's then kind of natural to think of some kind of coherent state, some kind of macroscopic configuration of a very large number of these atoms of space in some kind of condensate. And so this is the idea that I'll be exploring in the rest of the talk. And more concretely, I'm working in the setting of group field theory, as I mentioned, which I will show in a minute. But what we can basically do then in this setting is at least these three things that I'm listing here. So the first thing was basically what I discussed already, deriving some kind of effective cosmological dynamics from quantum gravity. There are many issues that have been discussed also over the years in the literature in loop quantum gravity. The meaning of the continuum limit, or breaking or deformation of symmetries, and so on, which you can study in these models because they are rich enough, because they have already a large number of degrees of freedom, and all these issues are completely absent in mini superspace, because there you just don't have enough degrees of freedom. And then also very importantly, if we want to connect to observation, we also need a framework that's rich enough to include cosmological inhomogeneities. So I will come to that towards the end. So yeah, I should talk a bit about what group field theory is at this stage. So basically, in one sentence, you could say that group field theory gives you a quantum field theory language for simplicial geometry, which is a certain type of discrete geometry. And it's also one way of defining the kinematics and the dynamics of loop quantum gravity. You can also come from a different direction and view it as a generalization of matrix models and tensor models in a way that I'll make clear in a moment. So what you have, at least in the formulation that we're using here, is basically a complex scalar field. So a standard quantum field theory of a scalar field, which is defined, which kind of is a function on this quotient space here. So G is some Lie group that you fix for the model, and you take 4 copies of the Lie group, and you have this kind of quotient space where you kind of have this group action on the right on these 4 copies. And what I mean by that is basically a diagonal action. So you can think of this field as a function of 4 copies of the group G, which has this invariance that it's invariant if you multiply all these elements, all these arguments from the right by the same group element. And G itself is chosen in such a way that it basically represents the local gauge group of gravity. So you think of a theory of gravity in terms of some spin connection, and that gives you a notion of local gauge symmetry, and that's implemented by this choice of G. So in 4 dimensions, you would typically choose SL2C, the Lorentz group, or you would take a rotation group in 4 dimensions, or if you want to do basically Ashtika variables, you can choose SU2. And the interpretation of these group elements is basically the variables. It's very similar to the variables of lattice gauge theory. So these are basically finite parallel transports of the gravitational connection that you associate to 4 links that basically are associated to the elementary excitations of the quantum field. So basically, because you have a quantum field, you can picture the excitations as some kind of particles, and in this simplicial geometry language, they're tetrahedra because these are the elementary building blocks of geometry, and you can then associate these group elements to kind of 4 links that go through the 4 faces of this tetrahedron that give you some notion of parallel transports. So that's where these group elements come from. So it's important to keep in mind that this space has nothing to do with space-time or physical space, but it's more like this auxiliary space of connection degrees of freedom that we're associating to to the excitations. In this sense, it's also generalization of a matrix model or a tensor model where you would just have indices here instead of these arguments that actually take values in a continuous group. Okay. You can make all this more concrete in a canonical formalism that we're using here, which is very similar to or closely related to the Hilbert space structure of loop quantum gravity. So you start with some kind of Fock vacuum. So this is completely standard Fock representation of a scalar field theory. So you start with this Fock vacuum, and the meaning of the Fock vacuum in loop quantum gravity would be the Ashtekar-Lewandowski vacuum. It's often referred to as the no-space vacuum. So it's a completely degenerate geometry. You can think of it as basically zero-metric if you want, loosely speaking. So there's no excitations of geometry in this vacuum. Mathematically, it's defined by being annihilated by this field operator. And then you impose these kind of standard non-relativistic commutation relations. So here I just have to make sure I can't just put a delta here because this has to be compatible with this invariance of the field under the right action of the group. So it's some kind of group average delta, but you can kind of ignore that. So these are the commutation relations that you impose. And what this means is that you can basically think of phi as a superposition of annihilation operators and phi dagger as a superposition of creation operators. And so then when you act on the vacuum with phi dagger, you basically get this, which is the tetrahedron that I just mentioned. It's basically your atom of space or your elementary particle, if you want, in this kind of Fock space. And here I'm labeling all these links with group elements, as I said before. And if you know about loop quantum gravity, this is an open spin network vertex, which is 4-valent. And then you can you can keep going and act with phi dagger to create more and more particles, and you get a standard bosonic Fock space of discrete geometries that are basically made up of that kind of stuff that we're using here. And the proposal is now to think of some kind of condensate of a very large number of these degrees of freedom. There are many different ways in which you can do that, so there's a pretty large freedom in defining this state. What I'm presenting here is just the very simplest choice that basically in the, if you go into a textbook on Bose-Einstein condensate, that's a good point. Well, these are chunks of geometry. I find it hard to think of them as fermionic. So I want them to be. It could be exotic. I think people have studied these models also with exotic statistics, so there's literature. So this is basically the simplest choice. So I don't think it's really fixed. That's right. That's right. But I'm imposing these at this stage without any good external motivation. So yeah, that's right. Yeah, so what we're looking for is some kind of coherent state, some kind of generalized coherent state, which represents a condensate. So in analogy with what happens in standard field theory, what this means is that the field operator acquires some kind of non-zero expectation value, unlike the vacuum, the Fock vacuum, and it should have a very large particle number with respect to the Fock vacuum in order to be representing a kind of potentially continuum phase away from the Fock vacuum. So this is basically the simplest state of this sort that you can think of. So this is exactly the kind of state you would look at in the simplest case in condensed matter physics. So here you take the field operator, which is basically a creation operator. You introduce this function sigma, which is plays the role of a mean field. It's basically the expectation value of the field operator. And here you take the exponential. So this is, you can see directly that this is an eigenstate of phi. So if you act with phi, you just get sigma. So that's the expectation value of the field. And the particle number is just the integral over the modulus of sigma squared. So this can be as large as you want, basically. And you can picture this as some kind of gas of weakly interacting atoms of space. as I said before, this is just the simplest construction you can make, and it's kind of very naive because it ignores correlations between these building blocks. And in fact, you can construct more interesting, more complicated states, and you can also include excitations over the condensate, as you would do in condensed matter physics. How much time do I have? 10 minutes or something? Okay. So that's good. I just want to talk a bit more about how we now use this proposal. So far this is just an idea. I'm just writing down a state in this kind of discrete quantum gravity model. And of course there's some intuition behind it that the state may represent a reasonably good approximation to something that's physically interesting. But now I want to use this proposal to actually extract some information about the dynamics and actually connect to cosmology. So I don't want to go into too much detail, but just explain in general terms what we're doing. So of course a GFT model that you take from the literature is specified by some action, so some functional of the field and of the complex conjugate, and you can then derive formally these kind of general Schwinger-Dyson equations, which basically give you expectation values, or are expressed in terms of expectation values, where O is some observable, so some functional basically that you fix, and this basically gives you some relations between the endpoint functions of your theory. So this is completely general, and depending on what you actually choose here, and how complicated you choose these observables, you get relations between higher and higher endpoint functions basically. So again, if you want to connect this to condensed matter physics, you can just take the simplest case in which this is just 1, and then this would give you the Gross-Pitagevsky, which again is the simplest approximation to the dynamics. If you want to go further, you take more and more of these higher relations into account, but then you stop at some point, and this is basically your truncation of the dynamics of the theory because you're only focusing on these expectation values. What you get in practice is some kind of complicated, in general, some kind of complicated nonlinear, non-local differential equations for sigma, which is this mean field. So what I mean here by this subscript is that I've already chosen this particular state, for example, or this class of states if you want, and basically the free parameters are given just by this function. So what I have to constrain through dynamics is this choice of function. So then you get these equations for this mean field, and you still want to connect this to cosmology. So how do you do that? The point is that you can now compute expectation values of certain operators, observables, on this quantum geometric Fock space. So the simplest one, for example, you can think of is something like the total volume. You can just associate to any collection of these degrees of freedom, you can just compute the total volume, the expectation value. And then you could say, oh, if I'm in a homogeneous isotropic configuration, that should be proportional to the scale factor cubed in terms of cosmology. So that gives me a notion of scale factor, right? The total volume can change over time and associate that with the scale factor. Similarly, I can derive something that basically measures curvature, and I can associate that with the Hubble parameter, and so on. So that's how I can associate cosmological quantities to this kind of condensate. There are also things like the particle number, right? I can just count the number of atoms, and this, of course, has no direct classical analog in GR, but these quantities also exist in the theory, of course, and are very important. And what I then get is basically, from these equations, I get some kind of constraints between these expectation values. So what I get is constraints between quantities like the scale factor and the expansion rate, or the matter density, if I had matter in the model. And of course, if I'm in isotropic homogeneous universes, this would just be something like a Friedmann equation. More generally, it's some kind of effective Hamiltonian constraint. So in a way, basically, we're working backwards. We know what the quantum dynamics is, or at least we have a proposal, and we are trying to derive some kind of effective approximation in this condensate regime, basically, where this is a good approximation to a physical state. the point I want to make here is that there are interesting effects, direct effects of discreteness. So these kind of effective Friedmann equations depend in general also on the quantum numbers, for example, the number of atoms in the condensate. So I'm just giving one example here to illustrate this. So this is in a specific model and for a specific choice of state and so on, so maybe not to be taken too seriously, but just to illustrate the structure that we obtain. So what you see here, so the variables are basically the scale factor. This is a connection. Here you have the Planck length. N is the number of atoms. And this mu is also a function of the number of atoms. So it's basically scales like n to the minus 1/3. The first thing you find is that instead of the connection, you always get the sign of the connection together with this function here. And this is very, very well known from loop quantum cosmology. These are basically the holonomy corrections that occur because you don't have the connection, but only these finite parallel transports. But what's nice, I have this interpret these. First, it was that's another point I just wanted to make about inhomogeneities. So if you think about normal mini superspace models, you have a wave function of the universe, and that defines by construction basically quantum mechanics of a single universe, which is perfectly homogeneous. Here we have a very different picture because we have this mean field approximation for the condensate. So we get this mean field, which we've called sigma here, and it looks like a wave function to some extent. It's often called the condensate wave function actually in the condensed matter context. But in fact, this is more like, because you've already taken an expectation value, this is more like a hydrodynamic approximation in which you think of some kind of fluid. So here what you get is some kind of fluid on mini superspace. So you don't have a wave function for mini superspace, but you have some kind of fluid. So you have a probability distribution for many kind of patches, kind of elementary degrees of freedom that have a particular shape and the probability distribution. Space. Here, this is what you're looking for in cosmology because you can directly translate this classical statistical distribution, which is what you see in the sky. So in principle, capturing some this, and that's basically because we're already exciting an infinite number of degrees of freedom of quantum geometry instead of just the one homogeneous mode. Okay, I should probably come to the end. So here I just wanted to, I can be very brief here, I just wanted to be a bit more speculative. So one exciting scenario that's a possibility here is this idea of geometrogenesis, which is basically associated with phase transitions. So again, what happens in condensed matter physics is that you start with nice gas, and then at some point when you tune your couplings, you encounter a phase here, and kind of expect a phase transition between this nice geometry can't be described by a smooth geometry at all. So the point I want to make here is that these condensates of atoms of space in group field theory are our proposal for describing a macroscopic cosmological universe in discrete quantum gravity. I only talked about the simplest approximation. in which you take this coherent state of many atoms, which are all in some kind of common ground state. You can then look at this hydrodynamic approximation of the quantum dynamics to extract some kind of effective cosmological dynamics. And the conceptual picture here is that the universe is some kind of fluid on mini superspace. I showed, at least in one example, how we can compute generalized Friedmann equations from expectation values of observables in this field theory. And nice and very generic consequences come from fundamental discreteness, and these will have a direct impact on the phenomenology. Of course, there are many open questions. We have to make sure that this whole scenario is consistent with GR or some form of higher derivative theory, at least in some regime where it's well enough tested. We have to understand the stability of the approximations that we've made and where they break down. Related to that, the fate of the singularity. It should really be related to some kind of phase transition here, which has to be understood much better. And I think this is what Daniele will talk about later this week. We should really compute the spectrum of cosmological perturbations for some interesting models so that we can actually talk about relation to observations. And we need to understand much better how to incorporate matter fields and also talk about the cosmological constant. And of course, there's much more that we have to do. So thanks for your attention. Well, it's supposed to be related to full gravity, so it comes. Mm-hmm. That's right. Well, that's right. So this, maybe I should have stressed this more. So what I'm focusing on here is just the very simplest case in which I'm assuming the condensate to describe an almost exactly homogeneous and isotropic universe. This is a very specific choice of configuration. Of course, a generic state in this theory looks nothing like a homogeneous or isotropic universe, and then I can't talk about a Friedmann equation. Well, you can think of, I mean, this is a field theory, so you can think about the classical field theory, but what it means is not very well understood. Yeah, I mean, that's basically part of the motivation of this work, that, we have a complicated quantum theory of interacting degrees of freedom at the Planck scale, basically, and we want to look at some, effective large-scale physics. Here in the setting of cosmology, which you can think of as basically a highly simplified setting of, what could be more potentially more general universes. But we're starting with the simplest ones, which are interesting, which are basically FRW universes. But this, in general, should be much more general, if this makes sense. Mm-hmm. Well, the most important ingredient here is this additional equation of state, basically, this relation between the number of atoms and the scale factor, which is basically what you would compute in LQC through the lattice refinement procedure. So we don't really have a systematic way of computing that yet from the full theory, so we kind of have to put it in by hand, in which case you can reproduce existing models of LQC, but this really depends to a large extent on what exactly you choose. So it's a bit... I think we should talk about what you mean, which equation exactly. But so what we first did was kind of just to ignore these terms, and then choose a specific matter coupling, and then you reproduce exactly the simplest LQC improved dynamics models. But this is with a lot of assumptions, so these should be refined much more. Mm-hmm. This one? Yeah, that's the imaginary unit. So, right. So this is, yeah, that's right. So I kind of wanted to skip over this, I guess. So in these, when you take these expectation values, typically they can be complex. So the kind of, you know, in this hydrodynamic approximation, the kind of coarse-grained kind of macroscopic observables you define, in general, are not Hermitian, so they can take complex eigenvalues. Well, at this stage, this is to some extent not very well understood, but it's fairly common in quantum cosmology, even in the old kind of Hawking approach, that saddle points, for example, to the path integral are typically complex, right? You have these. Well, you start with Euclidean, but then all the effective geometries you look at as saddle points are typically complex. So they can have real sections which are Lorentzian or Euclidean, but typically they're complex. So this is fairly, I would say this is not too surprising in quantum cosmology if you're looking at some kind of approximation. What it means in more detail.